Okay, I'm trying to, I will try to make this lecture a very brief lecture. So in the morning, we were talking about general voltage regulation, and we have said that this DC supply here, it represents output of, rectifier and filter. So the output of your rectifier and filter, after rectifier output, it was like this. After filter, your output was something like this, more or less flat. After your filter, your output was more or less flat DC. It's almost equivalent to your DC flat line. Yeah, so it's almost equivalent to it perfectly DC flat line after filter. So we can represent it like a DC source, your output of a filter rectifier and filter. Now we said that when you have a transmission line fluctuation 230 volt peak value 50 hertz, this can change up to 240. Sometimes it can drop below 220 volts, something like that. So it can have a fluctuation, right? And also we said that in a parallel connection, in a parallel circuit, the voltage that will appear across one arm of the parallel circuit, that is between this to this, is one arm. So another arm here is, this is connected. In another arm, you have this resistance. So it's something like this. You have a series resistance RS here, and you have a parallel connection, a branch point, something like this. Your Zener diode, which is having a symbol like this, and your load resistance RL. So if the current passing through your load resistance is, let's say, here I use a capital letter, so let's use capital letter IL. Current passing through this Zener diode is, let's say, your Zener current, like we talked about in the morning, IZ. So the volt, it will be, circuit will be like this. So this will be from filter. You are getting this signal from your filter, so it's a DC, right? So now if you look at this, if the voltage here, the voltage appearing across Zener diode is VZ, right? The voltage appearing across Zener diode is VZ. So the voltage that will appear across the load resistance RL will be current IL into RL. Current IL into RL is the voltage that appears across the load resistance. The voltage that appears across the Zener diode is VZ under breakdown condition. So if your voltage coming, your DC voltage here coming from this filter circuit is greater than the breakdown voltage, the voltage across the Zener diode will remain VZ, the breakdown voltage. So the breakdown voltage VZ, as you see, this Zener circuit is in parallel connection with the resistance RL here. Zener diode is in parallel with the resistance RL here. That means even if you have 2 branches, 4 branches, or as many number of branches in a parallel circuit connection, in a parallel circuit, the voltage appearing across each and every parallel circuit arm, they are identical, they are equal, they are always equal. Okay, so if VZ is the voltage appearing across a diode, it should be equal to IL into RL. It should always be equal to IL into RL. Okay, now if you say that IS is the current passing through the series resistance here, IS the current passing through the series resistance, and from this branch point, some part of this series current, it flows through the Zener diode as IZ, and some part of this series current flows through the load resistance RL as IL. Okay, so the current through the series resistance is IS equal to IZ plus IL. Okay, so these are the two set of relations in this circuit. If you look at this circuit, these are the two set of relations which are valid always, because here this is your output of a rectifier and filter, rectifier or filter, and you are connecting a series resistance. So the current passing to the series resistance is Is, and there is a branch point. The current is divided split into Iz and Il. So I is equal to Iz plus Il. And here you are having Zener diode, and the voltage across Zener diode under reverse breakdown. See here, under reverse breakdown, the voltage across Zener diode is kept at constant value, which is Vz. So the voltage across the Zener diode Vz must always equal the voltage across load resistance, because they are connected in parallel here. The load resistance and the Zener diodes are connected in parallel, so they are equal like this. Vz is equal to IL into RL. Now, let us assume that there is a line fluctuation. Let's say 230 volt to, let's say, 240 volt, it jumps. So we are trying to prevent our instrument, that is our load resistance, from getting affected by this line fluctuation, because if you alter the current pass or the current or the voltage passing through the load resistance, then that could cause certain unrepairable damage in your electronic gadgets. So we are trying to prevent that. Let's see how this Zener diode, Zener voltage regulation can prevent that. So what happens is that when the voltage increases to this, we know that the voltage appearing across Zener diode under reverse voltage breakdown is constant, always Vz. It cannot increase. So if it cannot increase, you know that if I increase the voltage from 230 to 240 volt, definitely the series current Is will increase. The series current Is will increase. Okay, the increase of series current Is will result in increase of voltage drop across this series resistance. Let us call it series voltage. Series voltage will be series current Is into Rs, series resistance. Current into resistance will give me the voltage. So the voltage drop across this series resistance here, Is into Vs, will increase, because if the voltage supplied from this rectifier output or filter output is increased due to line fluctuation here, your series voltage drop, that is the current Is will increase, Is into Rs will increase. Okay, but since Zener diode is such that under reverse breakdown, the voltage across Zener diode cannot increase beyond Vz. So because of that, Vz value will remain constant. So Vz value will remain constant. And also know that in this parallel connection, the relation here Vz is equal to IL into RL, this will remain valid. So if Vz cannot increase, that means IL cannot increase. If IL cannot increase, what happens is that the increase of Is will be compensated by increase of Iz here. Okay, so let's say the initial value at 230 volt, the initial value of Is was, let's say, 2 ampere, and the current across the Zener diode was, let's say, 1.5 1 ampere, for example, 1 ampere. The current across the load resistance IL was, let's say, 1 ampere each, and the voltage across the Zener diode is equal to the voltage across the load resistance, which was 1 ampere into the load resistance, let's say 10 kilo ohm. It was, let's say, for example, some 10 ampere kilo ohm, right? So this might be too large. Let's say this is 2 milliampere. So this would be 1 milliampere. Let's say this would be 1 milliampere. So milliampere and kilo ohm. Milli means, milliampere means 10 to the power minus 3 ampere. Kilo ohm means 10 to the power 3 ohm. So if you multiply this two, this will result in 10 volt. All right. Or in fact, let me use this as 5 kilo ohm. If I use this as a 5 kilo ohm resistance, this will result in 5 volt. So the voltage appearing across the xenon diode and the voltage appearing across your load resistance, which is IL into RL, will be 5 volt. The voltage across your load resistance, that is IL into RL, will be 5 volt. Right. Now, let's say the voltage is increased from 230 volt to 240 volt. Because of the increase of this 230 volt to 240 volt, let's say your IS value increases to from 2 milliampere, let's say it increases to 3 milliampere. And because of the parallel circuit here, this is Zener diode and this is your load resistance RL. Because of the parallel circuit here, VZ cannot vary. If VZ cannot vary, this is your IL, this is your IZ. Since VZ cannot vary, VZ is a constant, and because of that, IL into RL, that is the voltage appearing across the load resistance, should also remain constant. In order to make this IL into RL constant, you will know that your RL value is 5 kilo ohm. So in order to make this voltage constant, IL should also remain 1 milliampere. IL should also remain 1 milliampere. Okay. So, but the increase of this series current will result in increase of your Zener current up to 2 milliampere. So that IS is equal to IZ plus IL. IS equal to IZ plus IL. Okay, so that can be done in a Zener diode without increasing the voltage. Here, as you see, the IV characteristics of a Zener diode at a fixed value of VZ, IZ can vary between IZ minimum and IZ maximum without altering your VZ value. So whatever line fluctuation will result in increase or decrease of series current IS in the circuit, increase or decrease of series current IS in the circuit, and that also subsequently result in increase or decrease of your IZ, the Zener current, without causing any change in the VZ value and the potential appearing across your load resistance, that is IL into RL. Because this diode, Zener diode, and the load resistance are connected in parallel. So because of this parallel connection, the voltage that will appear across your device or your load resistance will remain constant. Okay, that is how it prevents line fluctuation. So I'm hearing some other voice. Okay. Now, let us consider another possibility called load regulation. Load regulation means if there is any fluctuation in load resistance RL. See, sometimes when you connect your television and all, you are using your television or your radio system or any instrument, for example, your computer also, if you use it for a very, very long time, right? And your instrument, your electronic gadgets also, after using, let's say for 24 hours or so, it gets heated up. So when it gets heated up, all the circuit components like resistance, capacitors, and all, after they are being used for a very long duration, they get heated up. And because when there is a heat in the circuit element, the heat in the circuit element will alter the resistance, isn't it? Will alter the resistance of a circuit. So also let's during hot summer also there can be certain temperature fluctuation, and if you are using your machine electronic gadgets for a long time, that will result in heating up of all the circuit elements of your electronic gadgets. So when such heating takes place, uh, the resistance of the circuit elements like your inductor impedance, capacitor impedance, and also your resistance value of certain circuit elements of your electronic gadgets, they can change, isn't it? RL value can fluctuate. Load resistance, as I said today in the morning, it is just the equivalent resistance of your instrument, your electronic gadgets. So yeah, after long duration of use, they can vary, right? So let's say your load resistance value dropped from 5 kilo ohm to, let's say, 4 kilo ohm after they are getting heated up. All right. Now your line voltage is not fluctuating. Let's say your line voltage peak value is 230 volt and 50 hertz AC. That means whatever series current is, let's say it was 2 milliampere, like in the previous example, it will remain constant. Line fluctuation does not occur, so your series current will remain constant. Your series voltage drop, that is Vs equal to Is into Rs, also will be constant. It cannot change, right, unless you have a line fluctuation. So what changes we have here is your load resistance drop. Now in your parallel connection, here again this is your zener diode. Here is your load resistance RL. RL value drops now. This is your IL. This is your IZ. So we say that this relation will be maintained because of the parallel circuit here. This is the voltage across the zener diode. As long as the zener diode operates in the breakdown region, the voltage across zener diode will remain fixed at Vz, and your voltage across the load resistance should also be equal to your Vz value. So if RL is dropped due to heating, in order to keep the voltage across the zener diode, in order to keep the voltage across your load resistance fixed, what will happen is there has to be an increase in IL value, isn't it? There has to be increase in IL value. But we know that your IS value is fixed. Unless there is a line fluctuation, IS value is fixed. So in order to raise your IL value, the current across your zener diode will drop. The current across your zener diode will drop. So let's say without any voltage fluctuation, without any load fluctuation, load value, the resistance value fluctuation, let's say this was your IZ value. Now the load resistance RL value drops down. If RL value drops down, in order to compensate for the decrease in the resistance here of the load resistance, in order to maintain the voltage across the load resistance constant, you have to raise your IL value. So when you raise your IL value, since IS is fixed, IZ value has to drop. So this is your reverse current IR. So IZ value will drop down. This is your 0. Okay, reverse current is in the negative axis. This is your reverse voltage VR. IZ value will drop down from, let's say, here initially in the example also we have given that IZ value was 1 milliampere. Now in order to compensate for the decrease in the resistance, IZ value will drop down to, let's say, 0.5 milliampere, something like that. Okay, so when IZ value drops, IL value will be raised, and then IL into RL will remain constant. So by using this zener diode that operates in the voltage breakdown, you can prevent your instrument from getting affected by load fluctuation as well as line fluctuation. That is, they are called load regulation and line regulation. All right. So these are the things that I wish to explain. But I think I should stop. I thought I will continue, but as I promised, so all these things, they, even though they are very simple, I think I better do it tomorrow, so that at least you can have about 30 minutes to revise your unit 1, as you will be having a class test at 3 p.m. Okay, the marks you obtained in today's unit test will be counted for your internal assessment mark. Okay, I will stop now. I will upload the link, Google link, for your class test. All right. If you have entered your attendance, then we can exit the meeting. Stop.